is going to talk about zkShuffle. Yep. Yeah, thank you guys for coming. So today I'm going to talk about zkShuffle. It's a mental poker on SNARK for Ethereum. A little bit about me. I come from UC Santa Barbara. Before yeah, go cultures. Yep. Yeah. So at year 2020, I built the first zkML research, and after that, I joined Manta network for the private payment, also optimizing like MSM on Wasam, and built something for 0x Park. Okay, so at Manta, we are building something called Manta Pacific. Manta Pacific is a EVM native layer 2 ecosystem designed for zk applications. We use Celestia for the DA, also the Caldera for the OP stack, and we build the universal zk circuits. So what is Manta's universal zk circuit? Basically, our thesis is like, hey, there are many applications, they need privacy, right, using zk. However, it's very hard to write zk circuit for most developers, right? So basically, we provide the universal circuit so other developers can directly use our circuit to build whatever their depths, right? Like the private voting, like many kinds of on-chain, fully on-chain card or poker game, right? There are many things. We provide zk as a service. Also, we provide the Solidity compatible things, so people don't need to learn anything new. They just use the Solidity code, also the some TypeScript code in the browser. Yeah, we also provide the SDK, so people don't need to learn many things. Okay, I will provide a very concrete example called zkShuffle for as an example of our universal circuits. So basically, zkShuffle is a universal circuit deployed on Manta Pacific, designed for a fair, decentralized, and private fully on-chain card poker game. It provides this very simple contract interface like the shuffle state manager, also the base game. So basically, for whatever kinds of card game like the Texas Hold'em, like the Hearthstone, if you guys are familiar. So they have a central part which is fully on-chain shuffle and deal, right? In addition to that, they can have super different like game logic, like I mean basically they share something similar, but they also have something different. So what we have done is the central part for shuffle and deal. Then other developers can write only Solidity code to make it fully on-chain. Okay, so how does this zkShuffle works? Basically, the goal is to build a fully on-chain card board games with Solidity and zkP. There are actually a few problems. The first problem is how do you fairly shuffle a deck of cards? So basically, we have a bunch of people, like 3 people or 5 people. We don't trust each other at all, right? We also don't want to trust any centralized server. So we need to play the card in a remote way and make sure it's a fair shuffle. The second question is how do you privately deal the deck of cards? Yeah, actually this is a very important cryptography problem called mental poker. It has been studied for decades. And basically we built up this mental poker and make it on zk SNARK. So we have a few things. The first thing is zkShuffle setup. So before a game starts, everyone takes turn to, basically have some cryptography setup like the public key, private key. Then everyone needs to do one thing called shuffle encrypt. So basically, in order to shuffle the deck, everyone takes turns to shuffle the deck. The randomness comes from the user machine. It's not from blockchain. It's not any centralized server. It's from the user machine. So they have fully control. The third thing is called zkShuffle decrypt. So once we have a shuffle the deck, everyone takes turns to deal the card. Now let's talk about how zkShuffle works. Basically, suppose we have 3 players, Alice, Bob, and Charlie. They start with a deck of cards. It could be 52 cards, 1 deck, or 2 decks, right? So basically, everyone takes turns to shuffle the card. Like Alice gets the card from the blockchain, shuffle it, and Bob shuffle it next. So let's see. So how it works with Solidity. Now we have the contract. Also we have the player. So on the contract, we start from initial deck. It's just some encoding on the elliptic curves. So Alice gets this deck from the blockchain. It's just a simple read. Then on Alice machine, Alice can run a program called shuffle encrypt and generate a shuffled deck. Basically here, whatever order Alice wants. At the same time, Alice will generate a proof to say, hey, actually this is a correct shuffle. Like I only have I only have 4 A's instead of 10 A's, right? Because every card is encrypted. If they don't have a proof, no one knows what happened. Then Alice will submit this deck to the blockchain, store it on the chain, and send this proof on the blockchain for the proof verification. After that, Bob will get this deck again from the blockchain and verify, shuffle, it's the same story. Let's ask a few questions here. So what is the source of randomness? It's from the user machine instead of the blockchain or the oracle. So it does not have many trust assumptions. The second question is, why every player needs to join the shuffle? Why don't we only ask one guy to shuffle for all the people? Because they don't trust each other. So I have to shuffle by myself. The third question is, why do we need additive homomorphic encryption? So basically, we want to make sure, hey, whoever shuffles first does not have any advantage over other players, right? So it's a fair game. Now let's talk about the card dealing. So we start with card. There are 3 locks on the card because everyone has taken their turn to shuffle and encrypt, right? So basically there are 2 locks on each card. Then like Bob gets this card from the blockchain and remove Bob's lock. And Charlie remove Charlie's lock, and finally Alice can see the hand card. Again, we can see how it works with contract. And on the contract, we have the card, Alice read it, decrypt it on Alice machine, and generate a proof. Then this card is sent to the blockchain, and proof is sent to the blockchain for verification. So one thing I want to mention here is when Alice decrypt card on Alice machine, Alice can have the choice whether I submit the decrypt card immediately or later, right? Basically, there are 2 kinds of cards. One is the hand card. I haven't played. I know the value. I can play it whenever I want, but I haven't played. Other people should not know it, right? In this case, Alice just does not submit these cards to the blockchain. And another case is, hey, I actually want to play it. Only at this time, Alice will send the card value to the blockchain. Yeah, again, let's ask a few other questions. So first, when dealing card to Alice, what prevents other players or anyone else from seeing Alice's card? Because what Alice read from the blockchain is an encrypted card, right? So other people cannot know the value. The second question is, does the decrypt sequence have to be Bob, Charlie, or Alice? Actually, no. So actually, any order works because we are using the additive homomorphic encryption. This is actually very important because during card shuffle and encrypt, we have to choose a specific order, right? A, B, C, right? But when we deal the card, we may deal to Alice or Bob or Charlie. So let's say, suppose we deal to Bob. Bob should be the last one to decrypt, right? So this order is important. The third question is, when Alice plays her hand, what prevents her from cheating, like playing a card that doesn't belong to her? So basically, we require Alice to submit a proof for the card dealing, for the decryption, so people knows this is a correct computation. Yeah, I can talk a little bit a little bit more details on the gamma encryption, the additive homomorphic encryption we are using. During the setup, everyone generates a secret key, public key, and basically they aggregate everyone's public key together into a shared public key. And later, when they encrypt, they use this shared public key for encryption, and use the individual secret key for the card dealing. Also, we have the encrypt. So you see everything is a elliptic curve, and we have the decryption. So basically, people use something. This is the core for the encryption and decryption part. In addition to that, people also need to do the shuffle and check the validity of the randomness stuff. Let me talk about the performance side. So the performance is very, very important, because one thing unique here is players need to generate the proof on their machine. I mean, this is quite different from many other zk projects like zk EVM and many other projects. Basically, they ask. They have some super powered machine, they will generate the proof, right? However, this is not the case in our game, because users don't want to trust any centralized server. They only trust the randomness on their own machine. So we care about the performance on the. By the way, we are using Go 16. So you see, the first thing is RNSS constraints is like 200K for the encryption and 1.5K for the decryption. For the proof generation side, it's like 11 seconds for the encryption and 0.1 second for the decryption. So every time when people deal the card, it only takes 0.1 second. And this encryption is only done once before the game. And we can make it even faster with some other optimizations. This is a gas cost. It's like 2 million. So on layer 2, it's like every game, if we play a Texas Hold'em, it's like $0.3 or even less. Yeah, so it's kind of cheap. Yeah, actually, this is about the prototype and the security design. Prototype is easy, but production is hard. So we have more optimizations to actually make it work, provide a good user experience. One thing is called pipeline shuffle to hide the proof generation latency. So we have seen there are some a little bit latency for the proof generation, right? And our idea is like, hey, we actually don't need to submit the proof for the game to continue, right? So we can submit the shuffled deck first, people can play it, and later we can submit the proof. And if someone does not submit the proof, other people can challenge and punish this kind of story. The second thing is called optimistic verification to mitigate the on-chain verification gas cost. So on-chain ZKP verification is a little bit expensive, if we have a bunch of many proofs to verify. So basically, it's like the optimistic design. We don't need to verify until someone challenge. The third thing is like the point compression to reduce on-chain storage because on-chain storage is very expensive. It's like 20K gas per data, and if we can compress the elliptical points, the gas is smaller. Yeah, we have many more optimizations like this one to make it actually work. So if you don't want to interact with the contract interface, we provide an SDK. It's a TypeScript code runs in the browser. You can simply call it. It will send all the transactions to the blockchain. Yeah. Yeah. So some folks in our ecosystem, they actually built the Tesla Hold'em game with one deck using the zkShuffle. I can show you guys a very quick demo. So you see there are 2 players. They are waiting for the 3rd player. Now there are 3 players. Everyone takes turns to shuffle the deck. So now I have finished. Okay, player 2 also finished his player 3. Okay, everyone finished shuffle. You see it's pretty fast. Now people are dealing the card. Okay. Okay, so now everyone can see their own hand cards. This is a fully decentralized game. I mean, we don't have any centralized server. Yeah, you see, most latency comes from sending the blockchain. Sending the transaction to the blockchain. The zk part is fast. Yeah, so people can use zkShuffle to build other card game. You can imagine they need to write the game logic in Solidity, but they don't need to touch any zk thing. Okay, yeah, that's it for this demo. Let me see the next one. Yeah, actually, okay. So the demo was about trading card game with one deck. We can build more than that. For example, we can build the trading card games with two decks. So how does it work in this case? So we have two decks like Alice versus Bob. They are playing the Hearthstone. So Alice has Alice's deck and Bob has Bob's deck. Basically, Alice shuffle and encrypts the deck, sends the deck to the blockchain. So now other people cannot know the card value. And one thing I want to mention here is actually we can have two totally different decks for Alice and Bob, right? This is very common game design in the many trading card game like Hearthstone. People can buy some cards, can freely compose whatever card they want, so because Alice shuffle and encrypts this card, sends this card to the blockchain, there is a lock. Other people cannot know the composition of this card of this deck. Okay, Bob can do the same thing, and then Bob shuffle the deck, and Alice shuffle Bob's deck. In this case, we have to shuffle the deck because Bob has shuffled Alice's deck. Alice cannot know the order of his cards in this deck. Yeah, this is a shuffle for the game with two decks. The dealing is similar. People take turn to deal. Okay, yeah, that's all for my talk about the zkShuffle, bring card or board game fully on chain. I have the spec here. If you are interested in the technical details, you can take a look. That's all. Thank you, Jeff.
Now we open up for questions.
So first of all, amazing talk.
Thanks.
I'm just curious, let's say someone goes folds, right, and they rage quit because they were losing in poker, and they no longer participate in the dealing process. How do you handle that?
Yeah, this is a very good question. So, depending on when you quit, suppose you quit before the game starts, right? It's okay. We just regenerate the public key. Also, if you quit during the shuffle, it's also okay because people can reshuffle it. Right.
But I quit when I lose in poker. That's when I get mad.
Yeah.
When all my chips are gone.
Yeah, this is a very complex thing. So let's say, suppose we have shuffled the deck, and in the game you still have the choice to click fold. Then you don't need to participate anymore. Right. This is the most common case because when you fold, you will automatically deal all the remaining cards because you have left the game. Right. You just deal.
What do you mean deal the remaining cards though?
Okay.
You don't let's say on the third card, right? Oh, I hit nothing. I thought I was I had a pair of kings and 3 aces just appeared on the board. Right? So I'm out.
Okay.
Is there a way to get around this, or do we just need to sort of penalize the players for rage quitting?
Yeah, so there are some technically we can handle it. Like there are something called partial homomorphic encryption. You don't need everyone to deal the card. Yeah, it's possible, but we are not doing this yet because there are some like trade-off between how much trust do you want to have to other players. Like suppose we have 5 players, can we say, hey, 4 out of 5 will never cheat?
Of course they will, right?
Yeah. There are many questions like this. So currently we don't use partial homomorphic encryption. We require everyone to deal the card. That's why we are taking something like the economically intensive incentive to say, hey, do not do that. Wait like 10 seconds and click the fold, that's all.
that makes a lot of sense. Like even you could just maybe force them to lose all of their chips if they don't participate, right?
Yep.
That makes a lot of sense.
Yep. Also there are, in many like seeing like the trading card game, it's a 1 versus 1 game.
Sure.
Right, so there's no such problem in one-on-one. Yeah, thank you. Please.
So just adding on to his question, like, have you ever considered like keeping track of like giving the player a maximum of like specifics of the game, but maybe like 30 seconds? Like, how would you like if you were to implement that? Would you like keep track of the block time?
Yeah.
Given like 15 blocks, how would you keep track of like a time if you were to implement it like that?
Yeah, please like the block block number.
So you can continuously just track the block time. Wouldn't that just require continuous calls to blockchain? When a player submits a transaction, do an action, there is a timer restarted, and the next player have to take action before this timer expired. But the timer, how is that tracked? Is that on chain?
Yeah, it's on chain. It's on the block number.
It's just a block number.
Yeah.
But how do you? Sorry, how do you continuously just call the blocks? Is it just reading, or no gas calls?
Oh, okay. So because all the logic is fully on chain using Solidity, there are some built-in API like block number something to read the block number.
Okay.
Yeah. You don't need any centralized server or Oracle for this block number.
So I probably have one question. So you mentioned there is an optimistic approach we take when it comes to verifying proofs submitted by players. I was wondering whether that's purely because of the gas consumption on Ethereum, or if we are assuming on a super fast chain, we can verify all the proofs if we want.
Yeah, it's currently it's mainly for the gas cost constraints.
Okay, yeah, because the kind of worry I have is not everybody realize that they're getting cheated when they're actually getting cheated. So in order for people to realize, hey, I'm getting cheated, I need to challenge this guy. That might take a while. And then say, for example, somebody built a super fast poker chain with, let's just say, DEF, which is, like might be super cheap, and therefore it makes sense to verify all the proof. I guess we can take that route if we find a solution.
Oh, okay, got it. So basically, you're asking, hey, suppose I'm a non-technical player. I know nothing about the zkP. I don't know why should I challenge, right? So basically, people don't need to actively take action for the challenge. We build it. We just have built-in utility in the browser. It will run in the backend, keep pulling the data from the blockchain and verify it locally. If there are anything wrong, they will challenge automatically, right? So because it's like in all this card game, it's like people fight against each other, right? So they have the incentive to challenge other players in the same game.
But do they need like a stake in their, like if let's say someone cheated and just like slashed their stake or something?
Yeah, currently it's like because like in zk Hold'em, people have the chips by default.
Okay.
Right.
Yeah.
Yep.
So do they just lose the game if they cheat? Is it like some kind of a
This
period
like they will.
winnings or the pot until like the optimistic deadline for proof submissions, like fraud proof submissions, is over? Like something like that.
Yeah, they will lose all the chip
Why don't
scores.
we just do like proof aggregation, and then it's only like 290. What is it? 290k gas to do Ground 16 verification?
It's not 200K, depending on how many public input do you have.
Okay, for sure.
Yeah.
Got you.
Cool. Beautiful. So I guess no more questions, and thank you, Boyuan, for this wonderful speech.
Thank you.